ihasmath, and you're going to learn how to solve applied problems with exponential graphs. These problems tend to be quite a bit different to the applied problems with parabolas, where everything was about the features. Here there is much more focus on finding and interpreting tables, equations and graphs. Typically these questions come in two flavors, ones with whole numbers in the base and others with decimals. What they do have in common is that the context is generally growth or decay. Let's have a look at a first past paper question. Pause the video for a moment to read the question yourself. These kind of questions used to be really scaffolded, like this one, but in more recent years they have been more open. The first part is really easing us in here. We just need to plot the coordinates. While Hank measures only once a day, I'm sure the plants grow more or less continually, so it doesn't really matter whether we want to draw in the curve or not. The second question is about interpreting and extending the table backwards. As the area doubles from one day to the next, it will be halving going backwards in time. This means that when the plant was first noticed, it covered 1 square meter, and I need to write that down as an answer. This doubling is actually a scaffold for the next part. We know the base of the exponential expression must be 2. The asymptote seems to be the axis, so there is no vertical shift involved. Although I can't see in my graph where the special point is, this is easy enough in the table. When d is equal to 1, a is equal to 1, so there is a horizontal shift 1 unit to the right from 0, 1, and I can write down the equation. In these applied questions, people tend to use letters other than x and y, so be careful with this. As there is no vertical shift in the graph, I could also have used a few coordinates from the table for the regression function in the calculator. This last question is a classic that you will come across a lot. Sometimes it can be done using either table, graph or equation, but in this case the maximum area in both table and graph are less than 500. In this case, I could just extend the table and keep doubling until the number is more than 500. The method that always works is to pop the equation in the table function in the calculator. This has the added benefit that I can check whether my equation was actually correct. I can see that I get the correct values for 1 through 8, and 10 gives me a number that is greater than 500, so the answer is 10 days. Let's have a look at another example. Again, pause the video to read the question first. The first part is actually a common thing. You need to use the information in the text to fill in the gaps in the table. For the first 3 months, the number of visitors is 4,000, and we get the other numbers using the table function in the calculator. Notice that I ignore the first few values, as the equation is only valid after the first 3 months. The second part looks familiar. Again, we're just copying the coordinates into the graph. We can't be 100% accurate here, but we just do what we can. I'm not going to connect the points here because they represent the number of visitors per month, and there is no 3.78 months, for example. The next part is about which month has fewer than 2,000 visitors. I'm going to draw in a line in the graph at p is equal to 2,000, and I can see that the graph dips below this line during month 7. So the 8th month is the first with fewer than 2,000 visitors, and the park would only be open on weekends after that, so the answer is 4 months. This hint in bold to use the graph disappeared over the years. More recently, you would have been asked to investigate this using tables, equations or graphs, which means you could have read the answer from the table or substituted 2000 into the equation and solved it. This last part is about changing the number in front of the exponential equations from 4000 to something higher. This results in a vertical stretch so that the park is open on weekends for only 2 months rather than 4 months. This means that month 10 is now the one that has fewer than 2,000 visitors. We can pop this into the equation and see that 2,000 is less than some value a times 0.85 to the power of 10 minus 3. Put the equation in the solver of the calculator with an equal sign rather than the less than. A is equal to 6,238.749 something. As a is on the right hand side of the equation, it must be at least that. But we know that people are discrete, so we need to round up to 6,239 visitors at least. That was a tough nut, and to celebrate I'm going to write an answer sentence. While some of these applied questions can be a bit of a challenge, most of them are actually just linking information from tables, equations and graphs to the context. Good calculator skills are a real advantage here, and if you come across a question that just asks you to investigate without giving you much of a scaffold, just start by drawing up a table and a graph and take it from there.